do my little, you need to kill me. And kill your sound output also. Let me kill my, make sure my sound is killed because it could be me. So how are we doing if
because like that's the
yeah, but you got sound output. You need to kill your audio output. Okay, we should be good now. And make sure I'm good to go. All right.
Okay, so
let me just introduce you. So, well, part the reason I want to introduce is this is the first of a new series of talks that we're going to be intermingling with similar talks that have been happening for many years down at Tetherless World. These are, well, formally we are calling them data idea seminars. But we are, Kristen Bennett and I decided there's going to be tentatively kind of two different ways that we're going to do that. There will be idea talks, and there will be idea seminars. The idea with idea seminar is it might be a more formal type of event. With idea talks, one of the things we're looking for is interaction. So I know Alex has a lot of things to get through, and it's going to be a fascinating thing. But you should feel comfortable asking questions. A couple things, logistical things to note is we are streaming live out to the internet. The streams will be available immediately following the recording via YouTube. We've created a new YouTube channel in order to broadcast these, so that's pretty cool. It's a technology which we figured out down at Tetherless World. So today we're welcoming Alexander New, who's one of our who's a Math Ph.D. grad student, one of our stars. And with that, take it away, Alex. Thank you.
Yeah. So hi everyone. I'm going to be talking about the work that my advisor and I have been doing for the past year and a half-ish. And so the focus is like what we're calling precision modeling. And I'll get into like what that means. And we're focusing on two different types of problems. So we're focusing on regression problems, which is where you're trying to predict some quantity that's real value, so like someone's cholesterol level, and then risk analysis, which is where you're trying to see like is someone at risk for having a harmful condition. And so what the big idea we have is this idea of thinking with cadres. So what does that mean? Well, in machine learning today, we have a lot of different types of models. So we have something like linear regression. It's very simple and very easy to use. And then you have something like a nonlinear kernel SVM, or like a neural network that's very complicated. And like you can say you know what's going on in one of those models, but it's difficult to have like actionable insights from the inner workings of the model. So Kristen and I are like sort of staking out a piece of the middle ground where like you have a little bit of both. And our basic style of analysis is where we say, okay, we're going to take our population and we're going to divide it up into like a probabilistic subset that we call a cadre. And so it's probabilistic in the sense that given any observation, so given at any point in your input space, that point has some non-zero probability of belonging to any one of your cadres. So this isn't like a standard cluster where in like a k-means analysis, an observation is deterministically in one cluster, none of the others. This is something a bit softer. And then what we also really care about is we want to have models that are interpretable. And so one way of making interpretability easier is to have functions that are sparse in the input space. So that is to say, if you have a bunch of different predictive features, you ideally only want to use a few of them to determine what observation, what cadre an observation is part of. And then the final part of like the main theme is that you need to do this like target prediction and the cadre assignment simultaneously. Because if you do them separately, which is easier to do, then you can fail in some specific problems that I'll talk about. And so if you do them simultaneously, then you know that the cadres are chosen for this very specific supervised learning task. And so then we have two case studies, I guess you would call it. So one of them is in cheminformatics, where you want to determine the relationship between this glass transition temperature and a polymer. And so this is some number, and chemists care about it. They can a lot of things to us, and so they want to know it. And this problem is known to be nonlinear, so you can't just use linear regression or whatever. Then the other is this whole idea of precision health. And so precision health is an approach for disease treatment and prevention that takes into account people's variations in genes, environments, and lifestyle. So that is to say, if you're considering something like diabetes 2, depending on what your genetic makeup is, you might have more or less vulnerability to a certain environmental chemical or whatever. What this turns out is it turns out to be very similar to the Cadre analysis. We can also use Cadre problems for precision health. And yeah, so our solution is we're calling them Cadres. And so Cadres it's distinguished from a cluster because cluster has a very specific meaning in machine learning, and this isn't quite the same thing as a cluster. So I'm just going to start by doing some basics. I've tried to keep the amount of math in here to a minimum just because that gets dense. But if you have questions about what the math looks like, totally ask. So this is what we call our illustrating regression problem. And so it's a pretty simple task. You have a two-dimensional input. And so one of the dimensions is shown on the left. So that series of histograms. So basically, one of your inputs is from one of these Gaussian curves. And then depending on what curve an observation is from, then it's on one of three different regression lines, which is shown on the right. So on the right, the x-axis is the second input dimension, and then the y-axis is the target. And so your goal is to learn a rule that can predict y given x1 and x2. So you look at this and it's very clear how it works. So you need to figure out how the clustering process works and then how the prediction process works. And luckily, our model solves this problem. If it didn't solve this problem, then that would be pretty bad as a toy example. But and you do get a little bit of problems here. So on the left, this is basically just what we have before. So the model can correctly identify what cadre an observation is from. And the right, we have this noise because the Gaussian curves overlap to some extent. And so that means that you can't really distinguish between them from the data alone. So you can't solve this problem perfectly, but if you're restricting yourselves to approaches that are interpretable, this is about as good as you can get, and our model can do that. And it turns out that existing methods can have difficulty with this sort of problem.
In the earlier slide, you had something called gating.
Yes. I'm going to talk about what gating and emission is in a little bit. But so just the basics is that we call the gating process the process by which you determine what observation or what cadre an observation is in, and then the emission is how you predict the target value given a cadre. So what a default thing a default way to solve this problem would be, okay, let's first cluster observations and then let's fit a model to each of those clusters. And so the standard clustering technique is k-means. And so on the right, this is what happens if you cluster your data using k-means and then color by the results. So what you can see is that we haven't really recovered all of the cadres. And that makes sense because k-means clusters over the entire feature space. And so that means that it clusters over both the feature that you want to cluster over and the feature that you don't want to cluster over. And because k-means doesn't know what the target is, it doesn't realize that one of these features is important and the other is not important. So by clustering over more than is necessary, you learn the wrong grouping. And so then that means that any sort of piecewise linear technique, which is what we're trying to do here, isn't going to work. So if you fit a linear model to each of your clusters, you won't get anything good because fundamentally the clustering is wrong. And then even if you do something really, really fancy, like a random forest, which is on the left, you can't, it's it's clear that you have some sort of success going on, but it's not great. And so this is because the random forest is almost too powerful for this sort of problem. And so then it tries to learn structure that isn't there. And so you don't get very great performance. And so like neither of them really works, but our model does work. So hopefully you're at least slightly willing to consider what I'm talking about. Like clearly this is like a toy problem, so it's not totally representative, but we've shown a case in which some fairly straightforward and widely used techniques can fail for a fairly simple regression problem. So how can we try to account for this?
Can I ask a question?
Yeah.
So in the last problem, you basically were saying that if you consider the entire feature space, that if like your model works, right?
Yeah.
But is it comparable if you just use the only, like, so if you use k-means on like the one-dimensional space, is it comparable then?
Then k-means will do just as well, but the issue is that you don't know what subset of the features you want to cluster over.
So this is like a more like general model. If you just have a bunch of data and you just want to put it in and see what happens, you'll get something better than if you like actually dig down.
I mean, like, so if you know what features are important for clustering ahead of time, then this model isn't, our model isn't necessarily as good. But if you don't know what's important, then this is, but you think that not all the features are important for clustering, then this is where the Cadre modeling is useful. Yeah, so this is the beginning of the math, but it's pretty straightforward. So like I was saying earlier, like Oshani mentioned, the prediction function has two parts. So you have a series of emission functions and then a series of gating functions. And so then the gating functions are what give the probability of Cadre membership for an observation. So that's this G sub m of x. And then the emission functions are how you actually predict the target. And so that's this E sub m of x. So in our toy problem, the emission functions are what tell you what Gaussian curve you're part of, or sorry, the gating functions are what tell you what Gaussian curve you're part of, and then the emission functions are what actually predict that line once you know what line you're on. And so that's more or less what I have in the bottom. So this is just like a sort of standard regression thing where like you want your prediction to be what you would expect on average. So, but it's not super important. Like the most important thing is that the emission function is what tells you what Cadre you're in. Or I'm messing that up again. The gating function is what tells you what Cadre you're in, and then the emission function is what predicts your target. So this could be like a linear regression. It could be an SVM. It could even be like a neural network if you want to get like more complicated.
So is that capital E for expectation?
Yeah. So that's the expected value.
So in that picture, how do the Gaussians relate to the two-dimensional plot?
So the Gaussian, like all the points that have an x that have a value in this red plot, in this red curve, belong to this red line.
But how do you get a Gaussian from looking at the red line?
You don't. So the Gaussians just tell you what line you're on, and then once you know what line you're on, then there's a line that doesn't rely on the Gaussian feature.
So are the Gaussians like a probability distribution of some feature?
Yeah. So there's two features. So one feature is only used for determining what Cadre you're in, and then one feature is only used for determining what your target is. And so this is the feature that only matters for determining what Cadre you're in. And then this is the feature that only matters what the target, that only matters for predicting the target. Yeah, so it's a very contrived example in the sense that there's very clear distinctions, but we've found in practice that it's surprisingly useful. So now that we know like what the gating and emission functions are in theory, like what do they look like in practice? So that's what these two contour plots are. So on the right, we're saying that what we care about is, so what we're going to say is every Cadre has some center, C. And then if a point is closer to that Cadre center than to other Cadre centers, that is more likely to be part of that Cadre. So it's a standard clustering thing. And so that's what we're doing here. So these ovals are how close you are to the Cadre center. But what we're doing that's slightly different is that we're not using a standard distance, we're using a weighted distance. So in this particular situation, we see that the x-axis feature, as that increases, the distance gets bigger. So then that relative to the y-axis. So that is, in some sense, the x-axis is more important for determining what cadre you're from. And so this is Mahalanobis distance is the sort of technical term for it, because you have like a Euclidean distance and you're weighting each feature by a separate number. And so and what this does, it lets us perform feature.
Just a question. Can you tell us what the x-axis is and the y-axis is?
So in this context, x1 and x2 could just be your two features. So they don't have this is no longer like the toy problem or anything. This could just be a general
So
case.
why do you say x-axis is, the distance in x-axis is more important than y?
Because so as x changes, then we cross these contours more quickly. And so that means that it changes the distance faster by distance.
But aren't you creating the contours? Like, you know,
Yeah. So this isn't meant to be like this is just meant to show how the gating process works. It's not meant to be an example of a good gating process. Yeah, just like to try to like visualize how this like weighted Euclidean distance works. And so then on the right, or sorry, on the left, we have the actual decision boundaries. And so that's basically just if you take this distance and then divide it by the sum of the two distances. And so it says what I've already said, where like if you're closer to one center, then you're more likely to be part of that cadre than the other cadre. And so
if, just to sort of, if you call it sanity checking, but very, very crudely, we could imagine that these are centered in, say, two of the Gaussian distributions that you had in your toy example.
Yeah.
Okay.
But so in the toy example, these ovals would actually just be lines, because in the toy example, only one feature mattered for the gating process. And so you can change the other feature as much as you want, and it's not going to change what cadre the observation is assigned to. But yeah, so precisely. So like this point would be the center of one of the Gaussian curves, and then this point would be the center of another one. So this is, again, kind of complicated looking, but this is really just saying what I was just saying. So like if you want to be really fancy, you can say that this is a multi-newly distribution characterized by an ARD kernel. But all that really means is that you have a weighted distance and you can perform feature selection during that distance. And then the bottom is just, once you have your cadre, it's just a linear function. So it's just like a linear regression line, basically.
So the terminology gating and emission, are those your terms, or is that kind of a term of art for this type of thing?
It's based on this other similar-ish model called the hierarchical mixture of experts, which is from the 90s originally. So I think they use gating. I don't think they use emission though. Okay, so yeah, and so basically you have some like sort of complicated process to determine what cadre you're in, and then once you're in a cadre, it's just a linear regression function is like the basics. And then one other special thing here is this number gamma, and so gamma is a sharpness type of parameter, and so that is to say, as gamma gets really, really big, it's increasingly likely that this probability G sub n will either be 0 or 1 for any x. And then as gamma approaches 0, you approach something where you're not at all confident what cadre an observation is part of, and so you just say every cadre is equally likely. And so you can choose this sort of as an interpretation thing, where like if you think that these sharply defined cadres exist in the data set, then you can choose a very large gamma, and if you're not as sure, you can choose a smaller gamma. Then there's also numerical instabilities for like very, very large gammas, but I've found it doesn't matter all that much. If you set gamma to be like 10, then you can get pretty well-defined cadres that are reasonably well-behaved. Yeah, I think that's reasonable. And so then just like to clarify, yeah. So we have a bunch of different parts of this model. And so looking back, we have a set of centers. So each cadre has its own center Cm. And then the model overall has a set of weights D. And so then the weights D are what say how important any given feature is for the Cadre assignment process. And then we also have W. And so W is the, like, you could think of it as the numbers in a linear regression line, except you have one for each Cadre. So we have a set of linear regression lines, a set of centers, a single vector D that says how important every feature is. And then we also have a sigma squared. And so that's another like standard linear regression thing. So like if you say, okay, given an observation, I'm predicting the target to be this, how confident should I be that it'll be within this range? And that's based on sigma squared. And so then the annoying thing is that we also have a couple of hyperparameters that we can't learn directly from the data. The biggest one is this capital M. So that's how many Cadres we have overall. And so sometimes you can use domain knowledge to figure this out, because in some cases you think, okay, I think I really only have 2 groupings, or maybe I have like 5 or something. But other times you just have to choose it via like cross-validation. And then you also have 2 more hyperparameters. So the way that you ensure that your Cadre selection process and target estimation processes work well is by using something called the elastic net. And what this means is that you can just basically say, okay, I want as many of these numbers as possible to be 0. So like you could have an input that's 100 dimensions, but maybe only 2 of those dimensions are actually important for determining what Cadre an observation is from. And so then in order to incentivize that, you can choose alpha appropriately. And then lambda is just a general regularization strength, which is a standard thing from machine learning. And then finally, we have the sharpness. And because this is
So for those hyperparameters, if you don't know any of these things, like the number of Cadres or what to set for these, are they determined recursively?
I'm not sure what you mean by recursively, but like,
you know how like in a lot of, like for example, in like SPM, if you're gonna find the weight, right? You choose a weight and then you see how well it is. So you go back and choose a weight.
Yeah, that's what you would want to do. So recursively or like cross-validation or something. And so because this is a regression model, you would expect to minimize something similar to squared loss. So that is to say, like you want to try to make sure that your model fits every observation as well as possible, subject to the model form. But it turns out that this is kind of hard to do for the Cadre model. It just gets kind of ill-conditioned. And so luckily we have a upper bound on the squared loss that becomes tight when Cadre assignments are very certain. So it's pretty straightforward. And then we've chosen to use TensorFlow, which is mostly used for like deep learning problems, but you can use it for general machine learning. And so the advantage of TensorFlow is, one, it has automatic differentiation. So that means that I don't need to spend hours of my life figuring out what the gradients look like, which is really, really nice. And then also it has a lot of like easy support for good stochastic gradient descent solvers. So when you have very, very large data sets, then traditional methods can be kind of slow. And so if you use stochastic gradient descent, then that tends to be faster and about as stable. So TensorFlow is really, really nice for that. And then this model is on my GitHub. I only put it there like yesterday, so I think it's...
No, 4 hours ago.
So I think it should be usable by anyone who has like TensorFlow installed. But if you try to install, I have like an example analysis too, just using a small data set. So if you run it and it fails horribly, let me know.
Did we install TensorFlow on the other machines
I
in
don't
cluster?
think it ever happened. I haven't received any notifications.
Okay, I think I should double check into that. We've got TensorFlow installed on the IDEA cluster, but it may only be on one machine or maybe on multiple machines. I don't know. So we got a couple TensorFlow people competing.
Yeah, so currently I'm only using CPU TensorFlow. You can do GPU TensorFlow, and that's when you have like extremely large problems, that's a lot better. But I haven't had to deal with anything like that so far, so I haven't done GPUs.
Just really curious, did you end up solving the problem that you started with the glass transition temperature?
Yeah, so that's actually next. Yeah. That'll be very shortly. So then, if you're familiar with this notation, that's okay. If you're not, that's also okay. This is just a graph that says like how the variables interact, and so then. So we're doing a discriminative Bayesian approach in the sense that we give priors to our parameters, and that's how those priors factorize. But like if you're familiar with this notation, this is a compact way of describing everything I've said for the past 5 minutes. And if you're not familiar with this, then that's okay because you can just remember what I said.
So is the sigma squared a parameter for the Leibniz distance or a parameter for that?
So the sigma squared is the parameter for the noise. So like we're assuming like a standard like y. So the y given x is normal with variance sigma squared around f of x.
Okay, so that's used for the emission function?
Yeah. So it's used for the emission function. Okay. So are there any other questions about like the basic formalism or anything? Then we're going to start getting your results. So maybe that's better.
Wait, so I interrupted you when you were talking about the sharpness.
Yeah.
So what's that?
Yeah. So like for so sharpness when the sharpness parameter is very, very high, then it's very likely that the emission function or the gating functions are either going to be 0 or 1 over the entire input space. And if sharpness is very, very low, then all of the gating functions are going to be about equal. So you use some combination of cross-validation or recursion or domain knowledge to figure out how sharp you want your Cadres to be. But in practice, it works about the same no matter what if you choose a gamma that's within like 10 and 100, it works about the same. Does that answer your question? Yeah.
So I get that. I guess gamma is like pretty robust to changes, right? But what about like the other parameters that you just said? Like I know m is like obviously like you just gotta choose that, but you mentioned something else that I don't remember.
Yeah. So the other two hyperparameters are alpha and lambda. So alpha is in elastic net analysis. Alpha is traditionally set by the user because like the alpha. Basically, alpha determines a trade-off between results being very, very sparse and results being fairly stable. So L1 versus L2 regularization. And the convention is just to choose one based on how sparse you want your results to be. And then lambda, you do have to, that can change how things look like. So you do need to try like a couple of different lambdas once you've specified the other hyperparameters.
So I guess like, so gamma is pretty robust, but like lambda is not, and it's kind of sensitive, so you have to.
Yeah, it's like comparable to like the weight trade-off in SVM.
Yeah.
So,
So how is the elastic net used to? So the elastic net is used to find which features are relevant for deciding your Cadre distribution?
So the elastic net prior is put on both W and D, and so it will. So it's a regularization term that will encourage sparsity. Yeah.
Oh, is that all it's doing?
So it encourages sparsity in the final result, and then it also encourages stability. Yeah. Okay. Yeah. So now we're going to go back to that chem informatics case study that I mentioned at the start. So as a reminder, the goal was to predict this transition temperature of a polymer, and so this once you like cross this temperature, the polymers will undergo like a qualitative shift in their behavior, so that they might become like really bouncy or something. And if you know chemistry, you can use this transition temperature to characterize polymers, copolymers, polymer blends, and polymer miscibility, so like how well the polymers mix with each other. So this is like a useful thing to know. And so we got a data set from the chemistry department here at RPI, which is pretty small. So we only have about 260 observations, and then we have about 30 features. So this is, you can't just throw something like a neural network at this because it'll overfit like crazy, and you won't get like stable predictions. So you want something simple, but the relationship between the target and what you can measure is nonlinear, so you can't just use like a linear regression model. So we try to apply our Cadre models to this problem. So this is just a
Quick
benchmark.
question on the data aspect. What's the difference between validation and testing?
So validation is used to select hyperparameters,
Oh,
and then testing is used to guess like how well it generalizes. So this is just like a benchmark type thing. So we tried a bunch of different models. And so what we tried are the supervised Cadre model, then a k-means model combined with linear support vector regression. So you cluster your data, and then you fit a linear model to each of those clusters. And then we tried a kernel support vector regression, so nonlinear, and then a random forest, and then we did like a k-means clustering, and we fit a regression tree to each of those clusters. So pretty standard. If you look, we're the red ones. So this is mean squared error. So low is good. So the closer you are to zero, the better you fit the data's variation. And we're doing pretty well. Like, so if you choose m equals 3, which is what we went with, then we're the best. But because this is a small data set, you want to be careful about saying that, because there's a lot of like minor variations that can mess with things. But the good thing about this results are saying that we can beat simple naive models, and we're at least competitive with powerful nonlinear models. So, well, that doesn't matter as much as it might, because what we really do care about the interpretation aspect of Cadre modeling, and so that's what we're going to talk about next.
How do you fare like computational time wise?
So right now we're a lot slower than any of the competitors, which is what you'd expect, because they're all using like specially written code, and this is something that I hacked up myself. So it is a kind of complicated optimization program, so it's probably never, it's never going to be as quick as like an SVM, because you can do that in like, I think almost linear time. But it's not terrible, because the stochastic nature means that it's never that bad in terms of solve time. But yeah, so what we've noticed is that, so we have 3 Cadres. What we found that 3 Cadres were what mattered, and you learn a different model. So each Cadre takes over a different region of the target. So there are 2 Cadres, these blue circles and then the green asterisks, that both consist of polymers with fairly low transition temperatures. And then there's 1 Cadre, these red pluses, that has larger values. So we've split the range of target values into 3, where 2 of them are fairly overlapping, and then the other is kind of distinct. And so this is, the plot on the right is from the testing data, and the plot on the left is from the training data. So this is just saying that like this split exists in both the training and the testing data, so it's not necessarily an artifact of overfitting. And so that's pretty useful, because like if you can group polymers based on their temperature range, and that's a useful interpretation step. Now, what also turns out to be the case is that the distribution of features varies between the Cadres. So each of these points is a test, or is a training point. So for 2 different features. So we have this atomic valence connectivity, and we have this normalized atomic polarizability. And so both of these, in some sense, help chemists infer what shape a polymer is. I'm not a chemist, so I don't want to say that, but they're useful for inferring shape, and so that they're interpretable quantities. And so we can see that on the left, this normalized atomic polarizability, it provides a way of distinguishing between the 2 Cadres with small temperature values. So the 1 and 3 both had low temperatures, but they have very different distributions of this normalized atomic polarizability. And on the right, we see that this atomic valence connectivity provides a useful way of distinguishing between the low temperature Cadre and then the single high temperature Cadre. So we can do this sort of analysis where we group our points by their cadre and then look at like univariate distributions and get a feel for how these distributions vary between the cadres. Now, what also turns out to be the case is, just as we hoped, the actual cadre assignment mechanism, so the gating functions, were very, very sparse. Of the 28 features, only about 10 of them were actually useful for determining what cadre an observation is part of. So that's what the plot on the left is. So the bars are the coefficients of that vector D. And so we can see that our poly B chi V is one of the most important ones for determining what cadre an observation is part of. And then the poly B apol is not quite as important, but it's still useful because it still has a significantly non-zero value. And then we can also plot the cadre centers. So these bar plots are the C sub m's, so the center parameters. And we see that in general, these still vary by cadre. So it's like this is kind of similar information to what the distributions do, but I guess in a more compact form. But yeah, so you can look at distributions and you can look at parameter values to gain inferences about what how the cadre structure works and how these things vary. And then the really, really complicated one. So this is the set of all the W's for the problem. So if you look, the labels on the left are like the different features that we use, and then each clustered bar of 3 is the set of parameters for that particular feature. So you can see that the one on the bottom left, poly PEOE VSK1 or something.
VSK1.
Yeah, so each cadre used that feature in almost exactly the same way. So its coefficient was almost exactly 0.25 for each of the 3 cadres. Then in contrast, the one on the top, so poly Q Don, was very different. So the cadre with very high temperature values was found that very useful, because a small increase in poly Q Don would result in a very large increase of the estimated temperature if you're in that second cadre. And in comparison, the 2 coefficients for the small TG cadres are lower. So we can learn this distribution of, we can learn these sets of distinct linear models, and we can again like interpret how these differences impact what the predictions are and that sort of thing. So to summarize this portion, we can divide these cadres into interpretable models, and what features are important for determining, for predicting the target vary by cadre, and so you have variation in that. Are there any questions about like this portion? So like the specific chem informatics case study?
I was wondering if there was, is this like a specific set of polymers, or like, so what is it?
It's a set of like 260 polymers.
Okay, it's just a bunch of different polymers.
Yeah.
Do they have like equations that govern how they react to different temperatures and like inputs, like the inputs essentially? You know?
Probably, yeah, but I'm not sure.
Okay, because that might be like something good to
Yeah.
check against.
Yeah, so like the issues that each of the features is like a kind of complicated entity. And so maybe that information is already in the model and I just haven't realized it.
So what was the chemistry question here?
You're trying to predict this glass transition temperature.
Based on those features?
Yeah, based on this set of measurements.
And there's no like formula in chemistry?
Apparently not.
I knew that's in theory,
Yeah.
so I know something about that. But there are a lot of equations with but like you said, it's just really concise.
Yeah. So like people have been using machine learning to solve this transition temperature problem for a while. So I think people have had a lot of success with.
There's one problem
Yeah.
that it's very history dependent. So depending on history,
Yeah.
it's hard to understand the structures to know about history. So that's
So I think that partial least squares has been used to solve this problem relatively well, and somebody did something similar to what we did, where you fit a Gaussian mixture model to the data, and then fit a set of SVRs based on that mixture model. But yeah, it doesn't seem like there's like a fundamental equation that you can use to calculate the TG. Okay, so now you say, okay, this is one data set. Why should I trust that? There's a lot of data sets out there. Does the Cadre model work well in those? And the answer is yeah. So we have 3 questions basically. So will a Cadre model generalize well to new observations? Is it not going to overfit? Are Cadres stable? So like if you take a data set for some problem and learn a Cadre model from it, and then you perturb the data slightly, are you going to get a similar structure or something very different? And then are the Cadres interpretable? So like, can you show them to a domain expert and they'll say, oh wow, yeah, that means this and this and this and this. And so we're kind of going to punt on the interpretability for this benchmarking, because you can't really do it for like a lot of different data sets because you need the domain experts. But we'll talk about the generalization and stability. So I picked 7 data sets from the CI in the repository. So it's like a standard way to get data sets. And then this is what they are. So they range in size from fairly small to fairly large, and then the number of features also ranges from fairly small to at least medium. Like none of these is like a big data problem, but they're reasonably representative. And so to answer the first question, yeah, Cadre models do pretty well in terms of generalization. So what I did was I took each data set and I generated 20 different training test splits. And then you learn a model in the training data, you evaluate on the testing data, and see how well it does. And then I ran it against a bunch of competitors, so the nonlinear support vector regression, linear support vector regression, and then naive approaches, like I mentioned before, where you do a k-means model and then you combine it with something else. And so if you look at these, so the lines in each of these, the central horizontal lines are the mean test set accuracy. And then the error bars are based on the standard deviation of the accuracies. And then the colors are each model, and the x-axis is each data set. So what we can see is, like on the far left, the air quality data set, the Cadre model was by far the best. And then that's not always the case though. So like for the Parkinson's data set, the kernel support vector regression was the best, but of the more interpretable models, the Cadre model was better than anything else. So like these teal bars are right here, and they're the best, but the Cadre model, the red, is in a decent second place. And so for these data sets, we do achieve generalization that's at least as good as what you could get without going fully nonlinear, which is good, and sometimes we beat that.
You said those error bars were the standard deviation of the accuracy. So are they the standard deviation of just the set of accuracies you got, or the standard deviation of the mean of accuracies?
So like what we have is we have 20 different test set errors for the Cadre model for the air quality data set. And so I found the standard deviation of that.
So you didn't divide by square root of 20?
No. Yeah, so it's not I'm not using this to estimate the mean. I'm trying to get I'm not using this to estimate the mean test error. I'm just trying to get a feel for how spread out the distribution of test errors is. Yeah, so it's not a standard error. And so another question is, okay, well, if we find a Cadre structure in the training data, will it appear in the testing data? Because if you overfit on your structure, then you can't really interpret it because you're finding spurious things. And so this is a harder question to answer with a less satisfactory answer. But a very sort of like first step is we can say, okay, if in the training data, Cadre 1 was 30% of the data, Cadre 2 was 40% of the data, and Cadre 3 was 30% of the data, then we would expect those sizes to generalize to the test data set. And that does happen to be the case for these data sets that we've looked at here. So I did the same procedure where I found 20 different training and testing splits, and then I found the Cadre sizes. And then you can use what's called Fisher's exact test to compare the proportions, basically. And so then, and that gives you a p-value where if the p-value is less than 0.05, then at that significance level, you think that there's meaningful differences in the sizes. And if it's above 0.05, then you're less confident that's the case. And so what we can see from this plot is that only a few times out of each of my models was the Cadre structure proportions found in the training data not also found in the testing data. And this is admittedly weak evidence for a true stability of Cadre-ness, but it's some evidence which is useful.
So here, I'm assuming you have the same CMs, and then you're looking at the distributions of the same CMs across.
No. So for each different training and testing split, you get a different set of CMs.
So how do you say how do you compare the probability of C1 in split 1 versus in split A versus C1 in split B? How do you know that those C1s correspond to one another?
So what I've been doing is I sort by I arrange the cadres that like the first cadre is the smallest one, the last cadre is the biggest one, and so with that alignment, then you can have. Or no, sorry, no. So that's not the case. So I don't need to worry about the comparison because I'm only looking at the sizes for a specific instantiation.
So you're saying you have the same CM across different splits?
No. So
What do you mean same instantiation?
So you take a training and testing split, and then you find the Cadre sizes, and you compare the Cadre sizes between that training split and that testing split.
Oh, so
and then
you know the sizes.
Yeah. So if you look at the CMs, it is more complicated and not as positive. But in terms of like this basic evidence, then you do get good results.
So the problem with this p-value test, I believe, is the null hypothesis is that they're the same distributions, right?
Yeah. So what this is saying is that for most of these tests, we're failing to reject the null hypothesis.
Are you interested? So I have a similar issue in my research. Are you interested in working on a better hypothesis test?
Yeah. That's we're definitely looking for better ways to measure stability. And so I have one other type of measurement that's in the next slide, but it's also not great. So that's this. So this is a very complicated looking plot. But what's going on here is that we take our data sets, and for every data set, we generate a bootstrap sample of that data set. So we with replacement and get something that's the same size as before. And then we learn a Cadre model from that data set. And then we say, okay, of the observations in a given Cadre from a given bootstrap sample, do those same observations appear together in the same Cadre from a different bootstrap sample? And if you do that a bunch of times and do some other stuff, you call that the average best match, which is based on some paper we found. And so then that's what this whole thing is saying. So what this is saying, for example, is that when you only have 2 total Cadres and you're looking at the air data set, then the 2 Cadres you find are almost always the same thing. So there's a very, very high average best match. But as you increase the number of Cadres, then you start getting a lot less stable. So once you go to 3 Cadres, for the air data set, your average best match is only about 0.6. And then if you go down to like 8 Cadres, then your average best match is like 0.5 or something. And this similar-ish behavior occurs in all of the data sets I looked at. So when you have a fairly small number of total Cadres, then those Cadre structures are fairly stable. But if you have a lot more Cadres, then the space of good Cadre structures becomes very large. And so you're unlikely to recover exactly the same Cadre structure as before from a bootstrap sample. So this is not the best in terms of supporting the Cadre model, because you can't be guaranteed to get something that's very similar from a slightly different data set. But what is good is that for each of these bootstrap samples, each Cadre structure is about as good as any other Cadre structure. So that is to say, the optimization problem we solve to learn a Cadre model is highly non-convex, and that there are a large number of different local minimas that you can learn. But each of those local minimizers is about as good as any other local minimizer, which is a similar situation to like neural networks, where you have a large amount of non-convexity, but each minimizer is about as good as the other ones. So, so what this means is that like if you are in an actual interpretation problem, you could try like learning different models and seeing which interpretation makes the most sense. But if you and if you're lucky, then like you'll find something that does make sense, I guess. This is a pretty complicated plot. So are there questions about anything I've said here, anything that's like not clear?
Why is it that we know that all these local minimums are going to give us about as good of an answer as each other?
Only empirical observation. So in the case of neural networks, you can show under certain theoretical assumptions that each local minimizer is exactly as good as every other local minimizer. Like using like proofs and stuff. But I have not tried to replicate that analysis for my own work, and I'm also not sure that the theoretical assumptions that are made are applicable to real data sets.
I was just thinking about a good way to put this into context would be to show what the expected best match would be if you had random Cadre assignments.
Yeah,
I think that would go to 0 very quickly.
Yeah, that would be a good way of showing things. Yeah. Okay, so to summarize this portion, we get good generalization with the Cadre model, but we're not guaranteed to find similar structures every time we learn a Cadre model. So it's a bit of a trade-off. So like the non-convexity of our model gives us a lot of predictive power, but it also means that we have to be careful about like assuming that one Cadre structure is the true Cadre structure from which all others are measured. And despite this, like a given instantiation of the Cadre model is interpretable, and like a nonlinear SVM is not interpretable. So we still have some benefits in that respect. So how are we doing? Okay, should I?
Finish up.
Okay.
You're fine.
So then the final portion of my talk is for this risk analysis in the context specifically of precision health. So what does risk analysis mean? Well, you say, okay, I'm a 30-year-old Hispanic woman. How at risk am I for diabetes 2? And then, so that's like one question that you can ask. So you assign observations a risk score for having a condition. And you can also answer questions of the form, okay, this is some pesticide that everyone on CNN has been talking about, and they're saying that it's bad for you. Does it actually have a measurable effect in causing diabetes 2 or something like that? And so you're trying to learn what factors are important. And so in machine learning terms, risk analysis is a combination of classification and feature selection. So you're trying to classify someone as either having a harmful condition or not having a harmful condition, and you're trying to say, okay, this feature, so this factor or feature is important for determining whether or not you're at risk or it's not important. And so we can do this with a Cadre model, because with the elastic net prior, we already perform feature selection, and then you can make the model do classification just by changing the loss function. And then the other sort of complicated thing that's going on here is that like in standard risk analysis, you want to be certain that your model is true and not just useful. And so you have to worry about things like whether or not a coefficient for a factor is significant or not. You want to have like a standard error for that coefficient. And we can't get that with a Cadre model just because of the non-convexity that I was talking about. So we do a sort of hybrid analysis that combines Cadre modeling with other stuff that I'll talk about. So this is kind of standard and not super important, but so we want to find what's the risk of having some condition giving my observations, and then we can quantify this like the risk of a feature with a p-value, where as the p-value gets smaller, we're more confident that an association exists. Of log odds ratio, so how like important is a factor for causing whatever, and then a standard error. So then how like if we change your data slightly and try to remeasure things, will we get the same thing? And to do this risk analysis, we're using a data set called NHANES, which some of you know a decent amount about. And so NHANES is a nationally administered survey. So it's administered the entire US population, which is cool. And it has a lot of different questions that let you ask other interesting questions. And so then we're focusing specifically on diabetes, which you can measure in 2 different ways, and they're not equivalent. And you have to choose like what years you're from, which is again like not really necessary for what I'm talking about here. But so what matters is that we have 8 different classes of biomarkers. So dioxins, metals, some other stuff, and each of those classes of biomarkers consists of a set of features, and we want to see whether or not those features are associated with diabetes too. And so to do that, we can use Cadre modeling. And we're going to combine this with a notion from statistics called a null model and a saturated model. So a null model is a supervised Cadre model that only relies on adjustment variables. So in our context, the null model only has access to a subject's gender, age, ethnicity, BMI, and socioeconomic status. It does not contain any information about biomarkers. So it doesn't use any of the factors we're interested in. And then the saturated model is the model that does have access to that information. And so then the idea is, if the saturated model is better than the null model at some statistical level, then we think that this biomarker is useful for predicting whether or not a person has diabetes too. And so then we have to do some kind of ad hoc statistics to answer whether or not this question is true, because like a standard approach would be something called a likelihood ratio test. And that doesn't work because of how we've set up our Cadre model, so we have to kind of make things up. But it seems to be agreeing with results that already exist. So this is what we do. So we learn a Cadre model from our training set. And then we say, okay, given all of our observations, what observation is part of what Cadre? And we also say, okay, using those saturated and null models, is the saturated model better than the null model? And so if that's the case, then we learn a logistic regression model, and that's what gives us statistically significant or accurate p-values, standard errors, and log odds ratios. So we use the supervised Cadre model to learn what the groupings are of the data, but we don't use it for actual prediction in terms of we don't use it to get log odds ratios or anything like that, because we want those log odds ratios to have standard errors. And then I tried this with 1, 2, and 3 total Cadres because that's just a reasonable thing to do, where we're not exactly sure how many risk groups truly exist. And so what these 2 plots both say is that most saturated models are not better than most null models. So, so each point corresponds to a different null or saturated model, or it corresponds to the difference between a saturated model and a null model's ability. So if a point is above these black lines, then the saturated model is better. And if it's below those black lines, then the saturated model is not better. And so for the most part, most saturated models are not better. And this is what you would expect. So if every single chemical out there caused diabetes in a meaningful way, we would all have diabetes, but we don't. And then we can measure this difference in 2 different ways. So that's why there's 2 plots. One of them is using a precision recall curve, and then the other is using a receiver operating characteristic curve. And then the points are colored by like what class of biomarker they belong to. So the dioxins, the metals, that sort of thing. Then we can say, okay, for those models where the null model was not as good as the saturated model, so when we were above those lines, we can learn our logistic regression models. And we can plot their log odds ratios. And that's what we're doing here. So what you'll notice is that in the cases where a biomarker, so a factor, was found to be significant in more than one model, in general, the log odds ratios are pretty similar. So what this is saying is that it's not like for some group of people, a biomarker is very, very, very effective at protecting from diabetes. And then in another group of people, that same biomarker is very, very effective at causing diabetes. In general, the distinction is either a biomarker is important for causing diabetes, or it's just not important at all. And so that's not something that we knew going into this, so it's an interesting observation. But that means that this is different from like the cheminformatics problem, where in that problem you did have very wide variation in what the model coefficients were. So that's an observation we've made. It's kind of interesting, and as we're moving forward with this, we're going to try to extend this to like new data sets. But then a useful question is, okay, what do these cadres look like? And so it turns out when you only have two cadres, the groupings are very, very interpretable. It's basically if you're very overweight and very old, you're in a high risk cadre, and if you're less old and less overweight, then you're in the low risk cadre. So that's what these two plots both represent. So the people in the teal turquoise curve are high risk, and then they correspond to the teal points in the scatter plot, and then you have low risk people that are red. So we have these very simple groupings that they're almost linearly separable using only two features. So going back to what I've said before, we gave the model access to a lot of features, more than just BMI and age. But what it turns out is you really only need those two features to determine what cadre you're part of, which is interesting. Then it gets a little bit harder with three cadres. So now you still have the high risk people who are more overweight and older, and you still have low risk people who are less overweight and younger. But then you also have this third cadre, the blue ones, which are like, basically they look like they should be low risk, but they're not. And that's interesting, and we haven't come up with a great way of figuring out why that's the case. So like you can look at other variables that look at like the other features we gave the model access to, and it's still not super clear. So that's like a thing to look forward in the future of why, of like what characteristics characterizes this these medium risk patients, I guess. And so then just to summarize, so we have a risk analysis framework. It integrates Cadre model and log odds analysis. We have a way of comparing null and saturated models, but it's kind of ad hoc. But when we have two cadres, at least, we do get very useful, very interpretable groupings that agree with findings by medical professionals. So that's good. And then that's everything, I think. Yeah. So there are other things we want to do, as you would expect. Are there any questions on the or anything like that?
So why are you only adding one bio feature? What if you need two bio features?
So that's an artifact of the data set. In general, it's hard. So people who have measurements for one biomarker are not guaranteed to have measurements for another biomarker, just because of how the survey is administered. So you kind of have to do it one at a time, which
You
is
should maybe describe that a little bit more, because NHANES is kind of peculiar in
Yeah.
that way.
Yeah, so that's like an artifact specifically of NHANES, and so it divides its subjects into groups, and then it divides those groups into subgroups, and depending on what subgroup you're part of, that determines what variables you actually have access to.
So how long have you been working on this for?
So the motivation for the Cadre model came from a work that my advisor did a couple of years ago. So she was looking at hospital revisits, and so what it turns out is that there's a qualitative difference between people who are very, very likely to return to a hospital emergency room after coming to it, and people who are not, in terms of like what reasons make you likely to come back. So like if you're like an alcoholic or something, you're very likely to have revisits. So she noticed that, like just by her own, she noticed that these cadres exist of the frequent flyers and the non-frequent flyers. And so then about like half a year later, we started working on like a way to figure out what the cadres are without knowing what they are. And so this has been about a year and a half. I've been doing NHANES for longer than that, but not from cadres specifically.
It's okay.
So I was curious about the approaches you compared to. So you said you had a bunch of k-means,
Yeah.
and then different types of regression.
Yeah.
Okay, did you try like a Gaussian mixture model or like spectral clustering and then regression?
You know, so we haven't tried that. That would be another useful way. So, yeah, so you could replace like the k-means with what that we've been using with like a more complicated clustering method.
And the second question, how about doing a regression first and then doing the clustering? So all of your competitive models were cluster regression. How about you do regression and then cluster on the output of the regression?
That's an interesting idea, actually.
Multivariate regression and
Yeah.
cluster in that way.
Yeah, that's.
I think that might be.
Yeah,
that's sort of what we use for the data thought.
Yeah, that could be an interesting way of doing things.
But obviously, you don't know how to do the regression.
Yeah.
Well, let's thank Alex.
Are you gonna make the slides available somewhere?
Yeah, probably.
Yeah, we'll figure out something.
Okay.